It's yet another death-Dalek style camping light, and I've not found any other yet, but I'm working on it. This is the third version I've found, and it's got the same extending body with the light inside it, but it's got the reflector light in the bottom, and when you click the button here once, I should actually have checked the button for being live before I did that, but let's go to that afterwards, because it is plugged in at the moment. So it's got the light in the bottom, you click it, it goes off, you click the button again, that clicks, and then you click it again, and they both go off. Actually, you know what? Let's check to see that button, if there's anything dubious in that, because, well, you know what we found out in the past. So I'm just going to reference this lead to the ground equivalent, not the actual ground, because I don't want to trip the RCD. No, the button's not live. That's a nice feature. Well, not live as we know. However, the output, the USB output that people are going to charge their iPhones in, if I plug this in here like this, noting that my body did become live momentarily there, because it's live at mains voltage, which isn't very good. Bit shady. Definitely not something you want to plug a metal-bodied phone into or finger too much. Note that when I'm doing this, I'm not referenced to ground, which means that although technically speaking my body's becoming live at mains voltage, there's nowhere for the current to flow, and therefore not much current is flowing. But I don't recommend doing things like that unless you absolutely 100% know the environment, because electrons will find whatever route they can back to their source. And ultimately that could result, if you tried that standing on damp concrete or in an environment where you know you did provide a route to Earth, you could get a notable shock. However, another interesting thing about this one that I just noticed, if I bring in a thermal imaging camera, I just noticed the top of it was warm. Now in this workshop is, well, I say the workshop is in the house, is not particularly hot. It's about 12 degrees Celsius, which is apparently cold. I don't know, it's fine to me. The top of this is quite warm, and I wonder if that's the batteries that are giving off a slight warmth. It was warm enough that when I touched it, it actually felt quite cosy. Oh, this is an E4, a Flirt E4. I bought it, not donated, I bought it full price from a supplier, but only because I kind of knew that it could be hacked, and I wanted to get in there before they fixed that little firmware issue that let you unlock certain features. So let's unplug this now, rendering it instantly safe, and let's actually pop this open. So let's see for a start. The bottom will unscrew, revealing the same style of reflector arrangement as the other one, where it's a star LED mounted onto the reflector with these little pillars and screws. I quite like that. It gives scope. There's a lot of slack wire in here purely because it retracts up when the thing is telescoped up. And this bezel is apparently just snapped on the front, and it has a switch inside it. Okay, that's reasonable enough. So let's open the other end, because it's where all the interesting bits are. Oh. So I shall pop that end back on. Oh, that's not going on terribly well. Oh, hold on. Almost there. There we go. So we'll telescope this down, and the last time to get into this, it was under the solar panel. So where's my spudger? Where is my spudger? There's my spudger. Spudger. Let's see if we can gently prise this solar panel off without destroying it. In the other ones it wasn't stuck on very well. In this one it does appear to be stuck on quite well, and is not happy about being released. Oh dear, right, okay. This is a bit disturbing. Oh no, there it goes. Well, it was going. It's making cracking noises. How much pressure do I use before my spudger suddenly changes shape? Right, okie dokie. And a screwdriver. Is this one going to fit? I think last time I had to use a smaller bit. I might even have had to use a completely different screwdriver last time because it was recessed down so far. So I wonder, given the connections between this one, the similarity between this one and the red plastic one, I wonder if it's the same circuit board inside. I guess we'll find out once it's open. So if this is the first time you've seen a video on one of these, it's a camping torch, but with slight technical issues in the sense that it uses what's called a capacitive dropper to power the output. I think this is the same circuit board as the previous one, but that unfortunately means that the mains input is effectively directly referenced to the output via a rectifier, and that means that when you plug this in, the output becomes live, basically at mains voltage, although it just appears to be roughly 5 volts. It's not actually 5 volts. Where's the little tester that I can actually demonstrate the voltage coming out with? I've lost the tester. There it is. This will not go in. I'll tell you what, let's lift this out completely then. So it's actually showing the voltage, it's actually showing about 5 volts. That's pretty good. I think that's probably an accident though, unless they've got extra circuitry in this, because all that's connected to is 3 AAA nickel metal hydride cells, I presume they're nickel metal hydride. That's just chance that you're getting that voltage, because it's more likely to be somewhere down to about, say, 3.6 volts. In fact, if I was to plug a load into this, I'm pretty sure it'd fall off quite quickly. So let's plug a load in. Oh, it's way down instantly to about 3.66 volts. At the 1 amp setting, let's see what the voltage comes up at. 4 volts. So really it is just nickel metal hydrides. There's no sort of voltage boosting circuitry involved in this. So I'm going to pop this circuit board out and then reverse engineer it. I've reverse engineered the other one, but it'd be worth seeing if there is any difference. I don't think there is. No, you know what? There's not a difference. It really is just what the last one was. So I'm going to cheat horribly and just go and get take a look at the last one, and that'll save me a bit of time, so I'll be back in a moment. I was wrong. It looks the same circuit board, well, similar style, but it's not. It seems to be custom made just for fitting in this case. And it's odd because so many of the design... hold on, I'm going to grab the other one. In fact, let's grab the other two. So, a lot of the design of this one was very similar to this one. And the reflector, is the reflector the same? The reflector is not the same. This one's more textured in the original gold Dalek light. I wonder if they all come out the same factory, they're out of different factories. Maybe they're all clones of a similar style. But here's the circuitry for this one, since it is different again. It's a similar circuitry, but it's a different circuit board. It's using the same approach as before. It's using a capacitive dropper, going through the bridge rectifier, and then everything is just in parallel in the output. A small token gesture smoothing capacitor, 220 volt, 220 microfarad, 16 volt. The USB port, the 3 nickel metal hydride cells. This little cluster of cells. Is that bigger? I think that's roughly the same size as the ones in the red one. Is it? It might actually be bigger. That'd be a good compromise. And then the switch, the oddity to this one is the fact that it has the 3-way switch. Now, what was the other one? Oh, no, of course, the other one only had one channel. Yeah, it's a 3-way switch. It's the one that you click it and it's got rotating contacts inside, and then it selects first one channel, then off, then the second channel, then off. And when it's connected to this LED, it's basically just pushing the nickel metal hydride cells directly out to that LED. Because under load, the voltage of the nickel metal hydride cells will drop to about 3.6 volts. And that'll push that LED quite hard, the high power one in the reflector at the end here. But it will be roughly about 3.6 volts, I guess. The other ones, when it switches in line, there'll be some losses along the wire, but the 5 LEDs that are used in in here, they are all just connected in parallel, and they're just directly switched again. It doesn't appear to be a resistor, which is similar to the previous one. The charging circuit, well, the charging circuit is different in the sense that the polarity is different from other circuits. Now, just for simplicity, to avoid lots of jumping wires, this denotes the negative here, this little block here, and it's the same for these two connections. So the solar panel is connected between the input here, from the capacitor through the bridge rectifier, and it's basically using this purely so it can light that LED. So it's going through one diode in here to the positive rail, and the negative is going through yet another diode. So once again, we've got 10 sections of solar panel here, but 2 of them are being voided completely by those diodes, because That basically means all you're left with is 1, 2, 3, 4, 5, 6, 7, 8, about 4 volts to charge the nickel metal hydride cells up with. And they'll typically float up to about 4.5 volt when they're fully charged. So unless one of those diodes might be, it might be a Schottky diode. Shall we check that if it's one of the low drop diodes? Let's put this to the diode test and see. If it's a standard diode, it will be about 0.6. If it's the low loss diode, it will be 0.2. So which diode is that? That is the, let's see, where is the diode? It's that one over there. Oh, this is not going to work. Oh, it's a standard diode. So that's just, it's not, they've just used generic diodes. I think one of the other versions used the 0.2 volt forward voltage diode just because it was going to make it allow much more efficient use of the solar panel. So that's how the solar panels connect to the batteries, basically via two diodes, the one inside the rectifier and the one here. And you think, well, why don't they just connect it with just one diode and put it in line here? And the reason is so they can light the charging indicator, because while this is charging, this little red LED lights. Can I get this little red LED to light? Yeah, there it goes. It's not very bright, but it's lighting. And that also means that the same red LED can light when it's charging via the capacitive dropper, because it is putting that drop across the... It's seeing the drop across the rectifier and the nickel metal hydride cells, so it will make that LED glow. And that's fundamentally it. So I wonder if there's going to be any more of these turn up. They've all got that shady feature that just makes them not really 100% ideal to have around the house, because while you know that it's going to be... the output is effectively going to be connected directly to the mains when you plug your phone or whatever into it. It means that people may actually be using these. They might have a plastic-clad phone. They may have a phone with a rubbery cover over it, and they've got it plugged in. They're none the wiser. But as soon as someone plugs in a metal phone or some other metal device, or they might even try checking the output with one of these little eBay testers, the sort of load testers, they're potentially in for a bit of a nasty surprise, basically involving a diode between them and the mains. So I'm not sure what to make of these. They're dangerous. They're not compliant with British standards or American or, well, European standards, any reasonable standard, just because of that one feature. So I wonder if it's viable then to make a little modification right now and stick a USB charging lead into one of these. I think that's a good idea. One moment, please. Okay, redesign complete. Modification is almost done. So let's take a look at the schematic first, and then we'll finish building the thing together and see how well it works, what sort of current it takes while it's charging, and so on. So here's what I've done. I've added a USB lead into the unit to charge. I've disconnected the mains lead completely. It's just not needed anymore. It's still there, and if anything, I've just used its little support pole as a cable tie to support a cable tie support for the cable. The new USB cable, which is permanently attached. It would have been quite nice having a little micro USB socket in that, but that's what we have. So the USB comes in, and there's a diode for, partly polarity protection that shouldn't really be needed, but also to prevent backflow into the USB charger, and means that if you plugged it in, but it wasn't switched on, or you just left the charger connected, it could gradually discharge the nickel metal hydride cells inside back without that diode. So it's kind of useful to have it. I also put a resistor now. I ended up using 5 1-ohm resistors in series here, which is a wee bit messy looking, but you know, it was just to spread the dissipation, because I thought, what's the worst scenario? Well, the actual worst scenario is everything going dead short circuit, and the 5 volt in would be across this 5 ohm resistor, which would result in the best part of an amp times the 5 volts is about 5 watts. So it'd be quite dramatic, and that would burn out these resistors. But in a normal scenario, that's the worst, case cataclysmic scenario. In the worst case scenario, the batteries are flat, but the lights, someone's plugged it in, but they're trying to power the LEDs. So with that, there's going to be about 2 volts drop across the resistors. It's probably going to be closer, 3 volts from the 5 minus the diode. It's probably going to be closer to 1.5 volts. So it would be a modest current, but the use of the 1 watt ratio, in this case I've used the 5 quarter watt resistors, means that they're never ever going to be stressed. I prefer things not to be stressed. I like a nice, laid back, reliable electronic scenario. So the incoming supply goes via the resistor and the diode. The resistor could have been up there, it could be anywhere in line with these wires here, just because, you know, it's just, as long as it's in line with the USB in, it will limit the current. Then we get the solar panel. The solar panel, this time all I've done is add a diode, and it's going to make it much more efficient. That means there's no LED, there's not an LED at all in this. In fact, the LED hole I put the cable in. However, that just results in greater efficiency anyway. It means that the solar panels are going to put everything into the nickel metal hydride cells. And in this case, here is the power module. This unit, if I turn it up to the light, is now charging the batteries. Simply, the solar panel is connected directly to the nickel metal hydride cells with that anti-reverse charge diode in it to prevent current going back through the solar panel when it's dark. So then it is just the nickel metal hydride cells. The USB port out, and this is the trickiest thing here, was the fact the wires coming up from the LEDs down here were really short. So I ended up having to twist them onto other wires and then tack them onto the USB port just as a support for the wires. That was the longest time taken. It was so footery because they kept on twisting as I was trying to solder them onto them. Very short tails, quite annoying. So the USB out, and then we've got those two tails going down, the really short ones, are going down to the LEDs, and it's the multi-way switch which has which switches between the big LED at the bottom, say, I think that, is it 1 watt, is it 3 watt? It might be. I think that's a 1 watt LED. The 1 watt LED off the 5, in this case I've just drawn 4 because I ran out of paper, the 5 lantern LEDs, which are this 100 milliamp large straw hat style. And then it switches back to the off position, so it just alternates between the two sets of LEDs. So that's the schematic. It's very simple. Let's make the last connections then, and put this module onto there and see if it bursts into flames or smoke ensues, as sometimes happens in projects when you've overseen something, you know, you've missed something really dodgy. So I'm going to flow a bit of extra solder onto this. I'm going to bring these pre-tinned wires up and I'm going to flow them on. I already have heat shrink primed and ready to go. I've mentioned it before, that annoying thing when you solder the wires and then completely forget you didn't put the heat shrink up. So I'm going to let that cool it with my fingers, in fact, that accelerates things. And then I'm going to slide the heat shrink up over that. Then I'm going to get the other connection, being careful not to short these two here, which I can't now because I've got the sleeve over the other one. Let's put another blob of solder in that, just so it's got a modest amount of solder, just to make it easier to flow the other one onto it. This is the thing where if you're not flowing the solder directly on to the solder joint, it helps to tin both leads and then reflow them together. And at that I see the lights in the base have just lit because they were turned on and are now being powered from the battery pack, so let's turn that off. There we go. Let's slip that heat shrink up. Get the hot air gun off my little cheapy Chinese Yihua 8786D station, because people will ask. This is such a useful thing. It's actually designed for reflowing solder, but it's really handy for doing heat shrink, and it's basically got a little 12 volt style fan in the back of here that blows air down a sort of heated core, and you can set the temperature on the unit, and then just look at I have just splashed solder in that heat shrink. Not to worry, it doesn't really matter. I was just making sure it wasn't a wee spike underneath. But yeah, you set the temperature and the airflow. So I have it set fairly low airflow because I don't need a high airflow, and it means that the thing is running fairly unstressed, which is always a good thing with Chinese products. They'll last a lot longer. The little Chinese soldering station, they're fine. I would recommend you get spare what they call soldering handles for them though. It's often just as cheap getting the full handle as it is getting the element. You just have to remember that when you get the soldering iron, some of them have the 5-pin plug and some of them have the 5 receptor, the female version of the plug, and you have to get the right one. So that's it. Technically speaking, it's back in action as the light, but now with the feature that it can be charged from USB. So let's plug it into USB right now. So this is showing 5 volts output. Let's see what current flows in. Well, not much actually. Why is that? Oh, you know what it might be? It might be because the batteries are fully charged, that the voltage has risen to... Hold on, let's get the meter. If the voltage is above approximately or in the region of about 4.4 volts, then it won't be able to put a charge into the cells. Oh, it is. It's 4.4, so the cells are pretty much charged, and in that instance, the nickel metal hydride, the USB can't put a charge into them. So if I then turn this on to put a load in it to bring it down a wee bit, it will partly be powering the LED in the bottom from the batteries in here, but now it's also taking some current from the USB port. So I'm going to let this discharge a while, so there's a reason to charge the batteries. So I shall choose the top light, and I'm just going to leave it for a while, and then come back and we'll see how much current goes into the batteries when they're in a more discharged state. Okay, I think that's had plenty of time to discharge. The LEDs have lowered in brightness, the battery has lost some of its charge. So let's plug it in and see what current it's drawing, and this time I won't cover the display, will I? So let's plug this in and see what it charges at. It's charging at about 120 milliamps. Going down quite quickly, I have to say. I reckon that these cells in this are not, shall we say, premium quality nickel metal hydride cells. I think they've got a fairly high internal impedance. Yeah, because the voltage on them is rising quite quickly. It's still a modest current. 80 milliamps would, it would... I get the feeling it would charge these at that in about 2 hours, unfortunately. I really have a feeling that the sort of cells they've used in these are the base model 150 milliamp hour, if that. The sort of thing you'd find in solar garden lights. So maybe that's the first viable upgrade for these would be to change those cells. Although having said that, of the best of these lights, the one to do the hack on would be this one, because it's got the separate battery compartment that, you could open this up to do the hack, but you could also just remove the cells from inside because they're very low capacity. And then you could just rely on it taking 3 AA's that then gives you the option of just charging them in an external charger. So, yes, in summary, cheap, novelty. Mains voltage a bit scary for plugging anything into the USB port because it will become live at full mains voltage via a diode. Yeah, what can I say? I wouldn't recommend buying them unless you want to actually just modify them or just get them as a sort of novelty gadget just to play about with. But just remember that when it is plugged in, that port is live. And if you put something like this in, it might not be so critical, but USB devices aren't designed for mains voltage. They're not designed with insulation for that. So particularly the metal-bodied phones, just be careful. And that's about all you can really say about the death-Dalek camping lights.